Is to go over Theorem 3.12, which says limit of 1 plus 1 over n to the nth power as n approaches to infinity equals 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorials plus dot dot dot, which is the sum of 1 over k factorial as k starts from 0 and ends at infinity. So we're going to prove this one. Actually, for example, let's say we have limits of 1 plus 1 over n, let's say 1 over 5 to the 5th power as n approaches to 5. Then that's going to be equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial, which you can write it as sum of 1 over 5 factorial as actually k factorial as k starts from 0 and ends at 5. So this equals what? 1 plus 1 plus 1 over 2 plus 1 over 3 times 2 times 1, which is 6, plus 1 over 4 times 3 times 2 times 1, which is 24, plus 1 over 120, whatever that is. Okay, so let's prove that. So let's say we started out with 1 plus 1 over n to the nth power. By using the binomial theorem, which you've learned in Algebra 2, this equals 1 plus n times 1 nth, or 1 over n, plus n choose 2 times 1 over n to the 2nd power plus n choose 3 times 1 over n to the 3rd. Do you start seeing the structure? And it goes on and on and on. And at some point, you'll have, towards the end, you'll have n choose 2 times 1 over n to the kth power. No, actually, this should be k. Plus dot 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 plus n over n times 1 over n to the nth power in general. So the right side of this equation, which is this guy, can be expressed as n choose k times 1 over n to the kth power. Each term can be written as that one. See that this guy, this power is the same as this number, and so each term can be expressed as this way, which is n choose k over n times k, because 1 over n to the kth power is 1 to the kth power over n to the kth power, which is 1 over n to the kth power. So that's why we can express in this way. Now if you take the limit of that, which we use the lemma that we just went over in the previous video, limits of this guy, which is n choose k over n to the kth power, as n approaches to infinity. This equals 1 over k factorial. So if you take the limit of this or this, then by lemma 3.11, it's equal to 1 over k factorials. Now this 1 over k factorial means 1 plus 1 over 1 factorial plus 1 over 2 factorials if you take the sum of it, right? So if the k starts from 0 and if you have 1 over k factorial, and if if it ends at if it goes on and on and on to the infinite in many power, that means 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorials plus on and on to all the way to infinity. Therefore, if you're taking the limit of this, which typical term is this one, and if you take the limit of it, then that's going to be the same as, so let me just write it down, right? So the limits of this guy, which is 1 plus 1 over n to the n power as n approaches to infinity. That's the same as these guys, which is 1 plus 1 over 1 factorial plus 1 over 2 factorials plus dot 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 all the way to infinity, which can be expressed as the sum of 1 over k factorials when k starts from 0 to infinity. Okay. By the way, 0 factorial is not equal to 0, but it is equal to 1, because if you say 3 factorial is 6, 2 factorial is 2, 1 factorial is 1, and 4 factorial is 24. You see that in order to get 24 to 6, you divide it by 4, 6 to 2, you divide it by 3, 2 to 1, you divide it by 2. So if you follow the pattern, we have to divide 1 by 1, which should be 0. So that's why 0 factorial is, I'm sorry, it's not 0. 0 factorial is 1. Okay?